Okay, thank you for the introduction. I'm here to talk about how we can use parametric mixers in different variations of optical signal processing. So I will start to describe the motivation behind the work we're doing and ways to implement it using the mixers and how we can create very nice combs and how we can do both frequency and time domain processing using these combs. So there is a need to be able to monitor very wide bandwidth in many applications, both in commercial and defense applications. Because if you want to find a signal that has very low probability to be intercepted by someone who tries to hide it, for instance, by make it frequency hopping or spread spectrum or some radar signal that are phase modulated, or so you need to stare at many bands at the same time. And in order to do that over a very, very wide bandwidth, which the challenge that's upon us is to cover the whole band from 1 to 110 gigahertz, is very challenging. So the ways of addressing this is that we can look at it both in a frequency domain way, where we call it channelization, or we can look at it in time domain, where we can sample it with optical front end and then follow by analog to digital conversion. And you can do it in either full band, which usually doesn't make sense, but you're mostly interested in a signal that is band limited into a smaller band, which in frequency domain you can filter it out, or in time domain you can subsample. So by the sampling theorem, you will bring the signal down to the first Nyquist zone. And why you want to subsample or to use frequency slices is that you want to marry the bandwidth of the best ADCs today to the full bandwidth that you want to look at. So let's start to look at processing in the frequency domain. So what you want to do is to look at signals monitored many frequency bands at the same time. Today, actually, most of the systems that are deployed on aircrafts or ships are actually scanning, which means that when you sweep the range where you're looking at, so you might miss signals that are out there. There are also filter banks that you stare at many channels at the same time, but to cover from 1 to 110 gigahertz is very challenging from a point of view where just the size of this wide range, and also to design the filters, because each filter will be unique for each frequency. So one way of addressing this is to use photonic technology to channelize the spectrum. Because in the photonics domain, you can decouple the shape of the filter and the frequency that you want to look at. And that's a very unique property. And we're creating a spectral signal replication front end, which you can do by either modulating frequency combs, or you can use parametric wavelength multicasting to take your signal to many different wavelengths and process them in parallel. So the one we are following, we're using parametric mixers. So we use nonlinear four-way mixing in optical fibers to create the means of doing this. So what we're doing is the first to implement the signal into the optical domain. And then it's followed by taking out slices of these many copies that we generate and effectively cover all the bands of interest. And this is enabled by us doing both the multicasting operation, but also creating a local oscillator comb that's complementary to this. So if we look at how we implement this technique, On the upper part here, we see the multicasting mixer, where you have 2 strong pumps and you have the signal that you want to analyze imprinted on one wavelength. These 3 waves are sent into the mixer, where we create many copies of the signal to different wavelengths. We also create a second comb, what we call the local oscillator comb, but it has a different pitch, so it slowly vernier walk over the different copies that we are generating. One key factor here is that they have to be frequency locked, otherwise you will not have a stable result. And then we can use coherent detection to receive each line and get the information in that frequency slice. An interesting thing about these 2 sets of combs is that we can, by changing the pitch of, for instance, the LO comb, we can change the bandwidth of the area we are covering. And in the same way, if we change the relative offset, we can choose which band that we're operating in, which makes this system quite flexible without changing the electronic backend at all. So other ways to generate frequency combs, which we've seen some examples of during the days here, is that you can use mode-lock lasers. But that is very well defined by the cavity, so you have a fixed grid, and it's not tunable. And you also have a limited amount of power in all the different tones that you're generating. You can also use electro-optic modulators to create your comb, but the bandwidth that you're generating will be limited by the bandwidth of your modulators, and also the signal-to-noise ratio will be limited by the loss that you have through your cascaded comb generation. And also with mode-lock lasers, you can create combs from megahertz levels to maybe tens of gigahertz, but you cannot reach hundreds of gigahertz pitch between the combs. But using parametric, we can reach those. So at UC San Diego, we recently developed ways of creating very broad bandwidth combs with high fidelity. And here is 2 examples where we have a pitch of 200 gigahertz, or a dense comb where we create 10 gigahertz pitch, but they're spanning more than 100 nanometers, and you can make them very flat in response, and here we show less than 2 dB. And there are so many applications you can use these combs for, and a few of them here is that I will show later, frequency domain processing. You can reference sampling systems. You can, of course, see this as carriers for a communication system. And if you have a dense comb, you can think of flex grid. You can also use 2 combs for ranging. And I guess you probably have other applications that could be used for these combs as well. So the principle for generating these combs is that we start with 2 CW lasers. And if we look in time domain, it's actually a sine wave that is generated by these 2 CW. And you can also look at the chirp, and of course it's unchirped at this stage. Then we go through a first stage of highly nonlinear fiber, where we create a chirp or 4-way mixing or cell-phase modulation, how you want to see it. But we create more spectral components of the signal. And in the chirp, in time domain, it doesn't change form, but we create a chirp. Then that's followed by what we call a compressor, which is the dispersive fiber, for instance, a single-mode fiber, which compresses this into a short pulse. And that is followed by a third stage of highly nonlinear fiber, which has a very flat dispersion over the range, so we can really explode the frequency comb generation. And one really have to carefully design all the parameters of the different stages to get it flat. But as I will show, it works pretty well for us now. So one principle of using this mixer is that we start with 2 CW lines. And in the mixer then, we have the advantage that we have no cavity, so we can freely tune the pitch of the comb that we're generating. A disadvantage of doing this is that there is no feedback process that makes the noise or line width being stable. So everything you introduce at the beginning will be spread throughout the comb. So you have to do something about it. So one way to control this is to use frequency referencing by injection locking. So by using a high-quality master laser, and you can use, for instance, DFB as a slave laser and use optical injection locking, we can make the DFB inherit the line width of DCL. So here we have the free running laser, and here is the injection lock. So we can see we go from megahertz to kilohertz level in terms of line width. And another interesting property of injection locking is that we can have the output being limited by the DFB, so the OSNR and RIN can be very low compared to the ECL, and also have high power, because high power is important to maintain high OSNR through a system. Here is an example if you use two fairly good ECLs that has a kilohertz line width and use them to seed the comb. And since they are free running, there is no control of how the line width is presumed. So as we look at copies further and further out, we can see that the line width is growing with a quadratic response, which is unacceptable in most applications. So by then instead using injection locking of two lasers to start with from a single seed, we can maintain the line width all over the comb, at least shown on this scale here. The way we generate these combs has been quite mature over the years, so we now can make this whole optical bench into a single box with just a turn-on switch that creates this nice output. And these combs can have very high OSNR and high power per tone. And just to show you an application of this comb is for instance, in data links, where you can use these as creating carriers for what you want to transmit. But you need to have high fidelity in the tones you're generating. So we also measure the phase noise, and we can see that the phase noise is fairly well confined all over the comb in C and L band. So we use this to try it with a 20 gigabaud 16 QAM signal modulated on to the carrier lines, and used a coherent receiver to measure it. And here we have the BR measurements from various lines all over C and L band. And we can see the performance is fairly similar. And if we look at BR to 10 to the minus 3, we can see that all over the comb it's within 2 dB variation from beginning of C band to all the L band. So how we can then use these combs for frequency signal processing. So we use this single master to injection lock the pumps in the multicaster as shown here, where we create all the copies. The second comb is generated in the same way, but with a slightly different pitch, so we get this vernier effect. We can then use AWGs to split out the different copies and local oscillators, and use coherent detection to receive the signal. So this is how we implemented the mixers. We have the upper here where we multicasted the copies. We show just a part of the comb here for proof of concept, and here is the local oscillator combs, and we used in this experiment 18 copies with a 1.2 gigahertz grid. And by doing that, we create a 21.6 gigahertz coverage, and we look at performance where we we change the frequency over the time. We can look at it in this frequency time plot. Or we made a little movie where we stare at all the channels all the time while we change this frequency to just show that it seamlessly moves over the different bands as expected. We also showed that we could change the setting of the comb by the agility of the system by changing the settings, so we also can cover higher frequencies. We went up to 75 gigahertz. And since we're using ADCs in the backplane, we can actually look at both time and frequency response of the system. So since I'm running out of time here, I just very quickly say that you can also use the frequency combs to time domain process, and we've shown this in the past where you can copy and sample all architecture. We use 2 mixers for multicasting and sampling, and we implemented this with the referencing, which reduces the crosstalk in the sampler, and we're now operating at 30 gigasamples per system. And we can use it over many Nyquist zones because of the bandwidth of the receiver. Here we see the drop in due to the modulator we're using. So to conclude the talk, parametric mixers can really enable signal processing of RF domain signals in the optical domain in both time and frequency. And I guess that concludes my talk. Thank you. You mean pump lasers, or? Yeah, I mean, we want as high OSNR as possible, and we need to injection lock them to stabilize the system. So high power is preferred. The more the better.